6.3 next, permutations and combinations. So what is a permutation? It just means a rearrangement of objects. For example, if you have the four objects A, B, C, and D in this order, you could think about changing the order, so rearrange them to, for example, C, D, B, A. So C, D, B, A is a permutation of A, B, C, D. But there are lots of other ways to rearrange four things. How many ways? Well, yeah, we can use the product rule. So thinking about so how do you rearrange things? Well, the first task is to figure out, so which of the four will we pick to go first? 4 ways to do that. Once you've chosen the first, then there are 3 options for the second, then 2, and then, well, there's no choice. You just have 1 option for the last. Okay, so by the product rule, it's just 4 times 3 times 2 times 1. That's 24 possible permutations for 4 objects. And this is what they look like. Yeah, so I made this list just going systematically, so that the first row is where we have A. Choose A for the first element. Once you've chosen A, then there are 3 possibilities for the second, so B, C, or D. And then 2 more options, so you can switch the last 2. Okay, so with an A, there are 6 ways to finish it. Starting with B, there are 6 more, C and D. Okay, so here are all 24 permutations of A, B, C, and D. Yeah, here's the one we saw earlier. Notice that A, B, C, D does count as a permutation, so nothing moved. This last one is everything reversed. Okay, so we're just permutations. We're just mixing up the order. We're also interested in permuting smaller numbers of the original objects. So suppose you just want to mix up 2 of the original 4 objects. Well, now you're choosing just 2 out of the 4, so it's 4 times 3 permutations. Okay, so that's 12. Here are the 12. So these are called 2 permutations. We're just using 2 out of the 4. And if you just want 1 permutation, so just choosing 1 out of the 4, well, yeah, there's no way to mix up one thing, so you just have 4 permutations of A, B, C, and D. In general, we use the notation capital P n comma r in parentheses for the number of r permutations of n objects. So far we've seen P4 comma 4 is 24. So these are all the 4 permutations of 4 objects. P4 comma 2 is 12. Yeah, 12. 2 permutations of 4 objects. And 1 permutations of 4 objects. Yeah, I hope it's clear that we get the same numbers if we were permuting objects for different objects, say W, X, Y, Z, or 7, 8, 9, 10. So it doesn't really matter what the labels are. You'll get the same. You'll always get the same numbers. And you can see what the formula is, just using the product rule. So the number of r permutations of n objects, well, by the product rule. So the first task is choosing the first out of the n, so n ways to choose the first, n minus 1 ways to choose the second, n minus 2 for the third, and then choosing the rth. Okay, we're ordering n things, r things out of the n. So the choosing the rth, there n minus r plus 1 ways to choose that last guy. You see that it's this number plus 1. Okay, so then this product, that's the formula for P and R. Alright, so we're just starting with n, go down by 1 at each step. There are r numbers in this product. That looks like a factorial. So remember the factorial notation with an exclamation point. So n factorial means n times n minus 1, n minus 2, go down all the way down to 1. Okay, so n factorial means the product of the first n positive integers, and also 0 factorial, that's defined to be 1. So another way to write our formula here is, if we continue, so the next number here would be n minus r. If we kept going down to 1, we'd have extra numbers, so we have to cancel so write this as n factorial divided by n minus r times n minus r minus 1 down to 1. So we have this factorial formula for the permutation numbers. Okay, example 1. 8 runners finish a race with different times. How many ways can the gold, silver, and bronze medals be awarded? So we just need the 3 permutations. So we don't care about who came 4th or 5th. So how many ways can we rearrange 3 out of these 8 runners? Well, that's P8, 3, so the number of 3 permutations of 8 people here. Okay, so we're multiplying 3 numbers together, starting with 8 and going down. So 8 times 7 times 6. So the answer is, yeah, there are 336 ways the medals can be awarded. Okay, and yeah, it's just the product rule. It's 8 ways to pick the winner. Then once you have the winner, there are 7 ways to pick the person coming second, then 6 ways for the person coming third. Okay, but it's just a permutation. Example 2, how many 4 permutations are there of a set with 10 elements? Well, that's P10, 4. So starting with 10 and going down, it's 10 times 9 times 8 times 7. So that's, multiply that up to 5,040. So yeah, so too many to list, but we can work out the number. Okay, so we're in this section. Yeah, here's the formula. Okay, example 6. Suppose that a saleswoman has to visit 8 different cities. She must begin her trip in a specified city, but she can visit the other 7 in any order. How many possible orders can the saleswoman use when visiting these cities? So yeah, so the first city, there's no choice, but for the remaining, yeah, we're permuting all 7. So we're looking for the 7 permutations of 7 objects. So yeah, so it's starting with 7 and going down. 7 times 6 times 5, 4, 3, 2, 1. And that's 7 factorial. And multiplying this out, 5,040. That's just a coincidence. It's the same number we got earlier. Okay, so lots of different ways to visit 7 cities. Example 7, how many permutations of the letters A, B, C, D, E, F, G, H contain the string ABC? Okay, so we're mixing up how many, that's 8 letters, but there's a restriction. We want the string ABC to stay we don't want to mix up these, we want to keep these together. Alright, so yes, you can think of this ABC part as they're kind of glued together, so this is just going to count as one object. And then we have 5 other letters, so they could be mixed up, rearranged in all possible ways. Alright, so yeah, so this question we have 8 letters, but we really only have 6 objects that we can rearrange. Yeah, so it's going to be 6 factorial, so 720 permutations. Alright, so I hope that made sense. Okay, next, combinations. So we already saw that there are 12 two permutations of 4 objects. If we don't care about the order of the objects in the two permutation, then AB and BA would count as the same. Okay, so if we don't care about the order, then there are only, out of the 12, there are only 6 different unordered permutations. And we use the word combination when we don't care about the order. So an R combination means choosing R objects and not caring about their order. And so we're using C's for our notation here. So C, N, comma, R. That's the number of R combinations of a set with N objects. So C4, comma 2 equals 6. So there are just 6 different 2 combinations of 4 objects. How about C4, comma 1? Well, if you're choosing, yeah, there are just 4 ways to choose one object out of 4, so yeah, there's no ordering possible. How about C4, comma 4? So now we're choosing 4 things, 4 objects from 4 things, and we don't care about the order. Well, if we do care about the order, there are 24 possibilities. But if we don't care about the order, then these really all count the same. So if you're choosing from A, B, C, and D, and you don't care about the order, then there's just one way. You just pick all the elements. Okay, so C4, comma 4 is 1. There's only one way to choose 4 things from 4 things if you don't care about the order of those things. Alright, so yeah, so that's the difference between permutations and combinations. Are you counting different orders, or do you not care about the order? And we want a formula, so C, N, comma, R Well, it's okay. We're choosing R things from N things. So if you care about the order of those R things, it's Pn comma R. But we're going to divide by the number of ways to mix up those R things, PR comma R. So this is like a division rule. If all the orderings really count as the same, then divide by that number. Okay, so this is what we want. So we're dividing by the number of ways to reorganize our objects. And then putting in the formulas, so this Pn comma R, that's n factorial over n minus R factorial. We're dividing by PR comma R, that's R factorial divided by R minus R factorial. R minus R is 0, and 0 factorial is 1. So it's this really just divided by R factorial. Okay, so the formula for CNR is the same as the formula for PNR, except an extra R factorial on the bottom. And this piece, this is the same as the permutation, so we can write it as just n times n minus 1 all the way down to this number. So we're multiplying R numbers on the top, starting with n and going down. So so just slightly more complicated. We have an extra R times R minus 1 dot 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 down to 1 on the bottom. Example 3, how many ways can you choose a committee of 3 from 8 people? So now this is a combination, because for the committee it doesn't matter the order of the people. You just want just a team of 3. Okay, so that's the key thing in these questions. You have to figure out, does the order matter or does it not matter? If it matters, it's a permutation. If it doesn't matter, it's a combination. So we need C8 comma 3, the number of 3 combinations from 8 objects. Okay, so on the top we need 8 times 7 times 6, so 3 numbers starting with 8. And on the bottom it's 3 factorial, so 3 times 2 times 1. And the best way to do this is don't multiply out the top and the bottom. It's much easier to cancel. So on the bottom we have 3 times 2 is 6, so these cancel, so we're just left with 8 times 7 on top, 56 over 1, so 56. And then answer the question. So there are 56 possible committees. Compare that with example 1. So here we're choosing 3 people from 8. We don't care about the order, so 56. But in example 1, we're choosing 3 people from 8, but we do care about the order. So that's more than 56, and there are 336 ways to choose 3 people from 8 if you do care about the order. Okay, so we didn't divide by 6 here, so So 6 times as many ways. Example 4, how many subsets of size 5 does the set T have? Okay, so this T has 7 elements. Remember, for sets, the order does not matter, so you just care about is the element in the set or not. You don't care about the order. Usually we list in increasing order for numbers, but this would be the same set if we switched the order around. Okay, so we're choosing 5 things from 7, and we don't care about the order, so that's a combination C7, 5. And by our formula, it looks like this. So 5 numbers starting with 7 and going down, and 5 factorial on the bottom. Yeah, these are big numbers, but we can figure this out using cancellation. So again, yeah, 3 and 2 on the bottom, so this 6 cancels with this. 4, the 4's cancel, the 5's cancel. So 21. And answering the question, T has 21 subsets of size 5. Okay, so if you're counting subsets, you need these combination numbers. Similar question here. Example 5, how many subsets of size 2 does T have? Yeah, this same T. Well, yeah, now instead of 5, we're choosing 2, so it's we're looking for 2 combinations. All right, so again, our formula, so 7, choosing 2 from 7, so it's starting with 7 on the top, but we just need 2 numbers, so 7 times 6, and on the bottom it's 2 times 1. So yeah, 42 over 2, that's 21. Okay, so we're getting the same number. Is that a coincidence? So choosing 5 combinations from 7 is, there were 21 ways. And that's the same as the number of 2 combinations from 7. And in fact, yeah, that always happens. So yeah, you can see. So choosing 5 things from this set. Well, if you choose 5, then you're leaving out 2. So choosing a group of 5 from 7, well, that's the same as choosing what's left out, so that's 2. I suppose I chose these 5 elements out of T. Well, I'm leaving out these 2. All right, so yeah, you can match up all the 5 combinations with 2 combinations, so it's going to be the same number of each. And in general, yeah, we always have Cn comma r is equal to Cn comma n minus r. And so the number of 5 combinations of from 7 objects is the same as the number of 2 combinations from 7 objects. The number of 3 combinations will equal the number of 4 combinations. Okay, these same formulas. Example 11, how many poker hands of 5 cards can be dealt from a standard deck of 52 cards? Also, how many ways are there to select 47 cards from a standard deck? Okay, so we're choosing 5 from 52. Do we care about the order? No, we just care about the cards we're getting. Yeah, the order doesn't matter in poker. Okay, so it's a combination, so the number of 5 combinations from 52. So it's 52 times 51. So these 5 numbers divided by 5 factorial. All right, yeah, so for this one, yeah, you could do some cancellation, but I think you really need a calculator. So we're getting 2,598,960. Okay, so yeah, lots of possible 5-card hands. Okay, and for the other question, so choosing 47 combinations from 52. Oh, well, by our formula, that's going to be the same number. Yeah, you can see it in the factorial expressions. It's the same. You just switch the order on the bottom of this product. But yeah, choosing 5 from 52, well, you're leaving out 47, so it's going to be the same number. So there are 2,598,960 ways to choose 47 cards from 52. Example 12, how many ways are there to select 5 players from a 10-member tennis team to play another school? Okay, so we're selecting 5 players from 10. Do we care about the order? No, we're just picking a team, so the order does not matter, so it's a combination C10 comma 5. So 252 possible 5-player selections. How about this one? So 30 people trained as astronauts to go to Mars. How many ways to select a crew of 6 people, assuming that all members have the same job? Yes, so we don't care about the order, so it's just C30, 6. And that's this number. All right, so we have this Cn, R notation. But yeah, there are other ways to write it. Yeah, these notations are also pretty common. And so we still have a capital C, but the N and R are moving around. But there is a very common notation that doesn't have a C. It just has parentheses with the N over the R. And this is usually called a binomial coefficient. Okay, so these choosing numbers are called binomial coefficients. We'll see why in the next section. Okay, but yeah, we're just getting used to this alternative notation. Example 6, compute 11, choose 3. So that's a good way to say it. Okay, so 11, choose 3. It's just C11, 3, so the same formula, 11 times 10 times 9, so these 3 numbers divided by 3 factorial. I can cancel 3s, cancel 2s, so that's 165. Example 7, how many bit strings of length 11 have exactly 3 zeros? Okay, so remember our bit strings, zeros and ones. Here we're looking at bit strings of length 11, so we want 11 zeros and ones. But we want exactly 3 zeros. So this is an example of what we're trying to count. So here the 3rd, 7th, and 9th bit strings are zeros. The rest have to be ones. Okay, so you can see we're choosing 3 out of 11 to be 0. Okay, yeah, the order doesn't matter, so if we chose the 3rd, the 7th, and the 9th, or the 7th, and 9th, and the 3rd, that doesn't matter, we'd get the same bit string. Okay, so choosing 3 out of 11, not caring about the order, that's C11, 3. So yeah, so just the same number, 165. Okay, and one more example. From the book, so in this one, suppose there are 9 faculty members in the math department and 11 in the computer science department. How many ways to select a committee consisting of 3 math faculty and 4 computer science faculty. So we're choosing 3 from the math department, so that's 3 out of 9. Do we care about the order? No, so we're just making committees like teams. The order doesn't matter. Okay, so there are 9 choose 3 ways to pick the math faculty. There are 11 choose 4 ways to pick the computer science faculty. Again, the order doesn't matter. And then altogether, yes, so it's the product rule. So our first task is how many ways to choose the math members of the committee. So it's that many ways. That's this number. Times, so the second task is choosing the computer science faculty, so that's this number. So it's this product. Okay, so 27,720 ways to make this committee. All right, so yeah, this last example was just combinations and then using the product rule to get the total number of ways. So again, think of tasks. So if you're making this committee, what are the steps you need? Well, the first step, choose the math faculty. 84 ways to do that. The second step, choose the computer science faculty. So this many ways to do that, and then it's the product of those 2. Okay, yeah, so we're doing some complicated counting.